In this video, we're going to go through the final section of Chapter 8 in the trigonometry textbook, which is the final section in the entire textbook, and is on parametric equations. So parametric equations is a topic that pops up in different subjects. So here in trigonometry, I talk about it at the end of the vectors playlist. We also talk about parametric equations in a good bit of detail in Calculus 3. And the reason why it's talked about in the vectors playlist and Calculus 3 is because parametric equations are directly related to vectors. In fact, any vector-valued function, you could technically consider a set of parametric equations. So, okay. The idea of a vector-valued function is that, so in a general sense, if we have any kind of function or relation, so remember, all functions are relations. Relations are any kind of, if you have inputs mapping to outputs, that's a relation. And a function is a special type of relation where all of the inputs are only mapped to just one output. That's it. Okay, well, we start by learning about relations in algebra with, one input, one output. And then we'll advance at some point to like two inputs, one output. And so any time this is just some relation, could be a function, or could not be, or maybe it's not. Any time there's just one output, you could have multiple inputs, but just one output, then we call that a scalar function. And we when there's multiple inputs or outputs, we think about those inputs or outputs as coming in the form of a vector. So if there's multiple inputs, say there's n inputs, then it comes in as a vector, an n-dimensional vector. And in any case, even if there's just one input, if you have a single scalar output, that's a scalar function. But anytime the output, there's two or more outputs, in which case you have a vector as an output, that's a vector function. So in general, you can have m outputs. M doesn't have to be equal to n. Now, this is completely general here. This is as general as it gets, because even, in real life, there could be some extremely complicated systems, nonlinear systems. Well, that's all going to be going on inside this black box here. You're going to send in some inputs, do whatever, and then out comes some outputs. That's it. Even if this is extremely complicated, it's still just a list of inputs and a list of outputs. All right, so why are all vector-valued functions, from a technical math definition perspective, parametric equations? Well, the reason is because the way you look at this is each of these outputs are like a function of the inputs. So y1 is a function of x1, x2, all the way to xn. Same thing with y2. Right, you could replace y1 here with some expression of x1, x2 to xn. I mean, it doesn't have to actually have an x1 or x2 in it, but just in general, you write it this way. Maybe that y1 is a constant, just 3. Or maybe it is something like 2x1 squared minus 3x2 plus 5x6 minus 1. This could be y1, and y2 could be something else. y3, something else, all the way to ym. Okay, so when you hear the phrase a set of parametric equations, for example, that's what this is. From a technical math perspective, this is a set of parametric equations with the parameters being the inputs, x1, x2, all the way to xn. Those are the parameters. And this is the set of parametric equations here. Maybe the inputs are the weight of a package and the volume of a package in terms of its size. That's the inputs. And the outputs are the price to ship the package and the shipping time. For example, that's the vector input, and then you have the vector output. The parameters are the weight of the package and the volume of the package. Okay, so all vector valued functions you can technically consider as a set of parametric equations, but not every parametric equation is a vector valued function. The reason is because even if we had a single input and a single output, like for example, x of t is equal to t squared minus 1. So in this case, it's like the t is the input and x is the output. Okay, well, this you can technically consider a parametric equation. This is a single parametric equation. Okay, so but in that case, what is this? Because like in that sense, I could say, all right, well, look, here's a parametric equation. Y is equal to x squared, a parabola. Like, what are we talking about here? Why are we using this name parametric equation or equations? Well, the way you want to look at it is, if you're treating an equation or a set of equations as parametric, then what you're going to be doing is you're going to be putting a window of focus on the outputs and kind of having the inputs in the background from like a graphical analysis standpoint. In the sense that, okay, with the weight of a package and volume of a package mapping to the cost to ship and the shipping time, maybe you don't want to label those two inputs as parameters. Maybe you want to treat those as just regular inputs, in which case you would just go ahead and do a three-dimensional graph. Let's say the inputs were weight of the package and volume of the package, and the output was the price to ship, cost to ship. Maybe you just want to do a regular 3D graph, input, weight, and volume of the package, and see the price and get this three-dimensional surface here and look at the relations between the three variables. But in some cases, like let's say projectile motion, trajectory, or other cases where the input might be something like time, well, in a lot of cases, we'd rather just have time in the background. In other words, just treat it like it's just a parameter. If you're thinking about the progression of some manufacturing system, all these different interacting components going on, then a lot of times we just want to watch that system progress without having the time parameter right in front of our face as part of like the graph and whatnot. That's confusing things. It's just a parameter in the background. And so if we're going to treat an equation or equations as parametric, then what we're going to do is we're going to take the outputs. Let's say we had 3 outputs here. We're going to take the outputs and graph or analyze strictly the relationships between the outputs and have the input parameters in the background. And so, like, again, why do we want to do this? What's an example of why we would want to do this? Well, what if the outputs were actually, X, Y, and Z coordinates? The input was time. So you had this vector valued function was to where that the X was a function of time, Y was a function of time, Z was a function of time. And so then the vector would be a position vector with X, Y, and Z coordinates. And for at any point in time, we could track the location of something in space with time. You see how time is in the background? We're just treating it as a parameter. And even in the simplest case of just a single input and a single output, you input a t and you get out an x of t. Well, if that's like the position along a line of something, we're viewing this parametrically, then with any point in time, we're tracking the x location of some particle or some object. You see, time is in the background. There's no time out here on this graph. The way we're analyzing or viewing this relation or function, the inputs are not included in our direct view of the outputs. Okay, and so now in general, the way a parametric equation or set of parametric equations works is this. So let's think about with an output of a three-dimensional output. Okay, but from 3 dimensions, you can abstractly extend these general ideas to any number of dimensions. So we've got a 3-dimensional output where the outputs could actually be spatial coordinates, but in general, they don't have to be. That is a common application to have actual spatial coordinates, and you're tracking the trajectory of something with the input being time. That's a very common application of parametric equations, but in general, this could just be anything. Y1, Y2, Y3, and the inputs could be anything you label as a parameter. Okay, so we have 3 outputs. There's 3 outputs. If there's just one input, a single input, then the result is going to be a parametric curve. And this is the way you want to look at it for any time there's just one input. No matter how many outputs there are, if you have a 5-dimensional output with one input, then you're thinking about a parametric curve in 5-dimensional space. It's going to be some curve, some parametric curve like this. And the way that you view this parametric curve when it comes to parametric equations, this is the case not just for parametric curves, but for any parametric scenario that we're about to talk about, you don't view the curve in this case, you don't view it as like a static graph in the same way that if we graphed a parabola, we would have this full parabola. You view it as you're at some location on this curve depending on what the input is. That's how it works, right? Depending on what the input is just x1, one input. Depending on what x1 is, that's going to dictate where we are on this curve. That's the way it works. And that's why something that's useful about parametric equations is that if you've got some relation that's not a function, then you can sort of like turn it into a function, because even though you have the same output corresponding to the same input in a sense, well, since it's parametric, you're going to be at that same output. Like if these two didn't pass the vertical line test, these 2 points, well, parametrically they do, because this is going to correspond to one x1, this is going to correspond to another x1. You see, you can parametrize a circle or like an ellipse, which is not a function in terms of its general equation. Okay, but if you parametrize it, then it is kind of like a function, because this is one time, or whatever the input is. This is a separate time. You're like traveling around the circle. You're following points along the circle. Okay, so again, no matter how many outputs there are, a single input, you're thinking about a parametric curve in that 3-dimensional, 4-dimensional, 10-dimensional space. Okay, if you've got 2 inputs, a vector of 2 inputs, let's say going into a 3-dimensional space, 3-dimensional output, where you can, once again, you can see we've put the inputs into the background. We can't see the inputs directly. Then in that case, you're not going to have a parametric curve, but you're going to have a parametric surface, some surface within this space. Surfaces are 2-dimensional. Curves are 1-dimensional. Surfaces are 2-dimensional. Now, you'll still need 3 dimensions to locate every point on this surface, right? Each of these points you need 3 dimensions to locate each point. So here would be the position vector of outputs, the y vector output, the output vector, okay? But the idea is for any x1, x2 input, you're going to be somewhere on this surface. And for all the x1 inputs, you'll completely go through all the entire surface. That's the idea. Again, we're not looking at this as like a static object. It's depending on what the inputs are, is going to depend on where the output vector is on the surface. And then you could generalize this to, if you were in, the output was 10-dimensional and you had 2 inputs, then you would be thinking about a surface in 10-dimensional space, a parametric surface. Okay, if there were 3 inputs, then you would have a parametric body, volume, where depending on what the input is going to dictate where you're located on the body. For all the potential inputs, you'll scan the entire body. If you had a 20-dimensional output with 3 inputs, you'd be thinking about a solid body in 20-dimensional space. And now, similar to how we abstractly extend geometrical features to n-dimensional space in linear algebra, well, you would do the same thing if you had a 5-dimensional input of parameters into a 10-dimensional output. You would just call it like a 5-dimensional body within 10-dimensional space. Okay, so now that we've gone through that overview, let's take a look at the start of the section. It says we have graphed sets of ordered pairs that correspond to a function of the form y is equal to f of x or r is equal to g of theta. So they're talking about the previous section here with polar coordinates. Yeah, so if we think about the definition of trig functions, that's sort of a polar type of graph, but I wouldn't consider that parametric because the input is a part of the graph, theta being the input. Right, based on each theta value, we can get a trig function. Cosine theta is x over r, sine theta is y over r, etc. But theta is a part of the graph here, the input. So that's not in a parametric form. All right, but it says another way to determine a set of ordered pairs involves the operations x is equal to f of t and y is equal to g of t, where t is a real number in an interval I. So yeah, usually the parameters are defined over some interval. You'll say t is less than or equal to 10, greater than or equal to 0, let's say. And you'll do the same with the other parameters. Each value of t leads to a corresponding x value and a corresponding y value, and thus to an ordered pair x, y. Yeah, so really the easiest way, in my opinion, to look at this is more of that. In this case, x and y are the outputs, and t is the input. You look at this as a vector-valued function. And we're going to plot strictly the outputs and leave the inputs in the background. That's the idea of when you treat a relation parametrically. All right, so now the parametric equations of a plane curve, what they're saying here is that it's a plane curve. So you're going to have, a plane curve. So for any parametric curve, there's going to be one input, no matter how many dimensions the output is the output. Now, but when we see the word plane, we know that means it's going to be a 2-dimensional output. It's going to be in a plane. Well, 2 dimensions doesn't have to mean plane, but usually it does. Like the default is 2 dimensions, like an XY plane. Okay, but remember, a parametric curve, you can have a parametric curve in 5 dimensions. If you had a curve is going to be one input. And it's going to be a planar curve if it's a 2-dimensional output. But then it'll be a curve in 5 dimensions if it's a 5-dimensional output. Okay, in this case, the parameter is t. That's a very common parameter with parametric equations because t is used to represent time, and you'll map out trajectories of objects, vehicles, etc. Okay, graphing a plane curve defined parametrically. Let x equal t squared, y equal 2t plus 3 for this interval of t. So now let's graph this. We know that there's one input, t. It's a 2-dimensional output, so it's going to be a plane curve. So what's the curve going to be? Well, first of all, remember, with any parametric equations, yes, we're going to get a curve or a surface or a 3-dimensional object. But it's not static, right? Remember, for every input, we're located at some point on that curve. And so how do you graph this? Well, you just plug in t is equal to minus 3, t is equal to minus 2, t is equal to minus 1, and get the xy pair. Because look, we're graphing x versus y, and there's no t visible here. We're just graphing the outputs. So when t is equal to minus 3, what does x and y equal to? Plot that point. We're at a single point. Minus 2, minus 1, 0, 1, 2, etc. You get a series of points. You can connect the dots to get a curve. Okay, but now what they talk about here is, for the same set of parametric equations, can we like analytically figure out what the curve is? Instead of just plotting points and connecting the dots, can we like eliminate the t here and just get this curve as a function of like y as a function of x? Well, yeah, you can do that because all we need to do is solve for t. and then like substitute. So if we take this equation and solve for t, so you have 2t plus 3 is equal to y. So 2t is equal to y minus 3. T is equal to y minus 3 divided by 2. So now let's plug this into x is equal to t squared. So x is equal to, you have y minus 3 over 2 squared. And there we go. So x is equal to y minus 3 squared divided by 4. 4x is equal to y minus 3 squared. And that's going to be a horizontal parabola. And that's exactly what we see here. Okay. So now this next example, it says to graph this set of parametric equations. And so we could plot points, but I guess it would be easier to go ahead and just convert this to the corresponding form where the two output variables are related. So y is a function of x. But this isn't so simple because it's, how are we going to solve for t? I guess take inverse cosine or inverse sine on both sides. That's kind of complicated. Well, here we can use trig identities. So x squared is equal to 4 sine squared of t. Y squared is equal to 9 cosine squared of t. Okay, and so with that, we see that x squared divided by 4 is equal to sine squared of t, and y squared divided by 9 is equal to cosine squared of t. Therefore, x squared divided by 4 plus y squared divided by 9 is equal to sine squared t plus cosine squared t, which is 1. And there it is. And we know that this is the graph of an ellipse. And there's the ellipse. But we also know that what this means is this is a parametric curve. So parametrically, for each t value, when it comes to the parametric equations, for each t value, we're located somewhere on this ellipse. And what you could notice is that this ellipse here is not a function, but from a parametric perspective, it kind of is, right? Because even though there's 2 points at this same, this doesn't pass the vertical line test, but these are 2 separate values of t with respect to the parametric equations. Okay, parametric representations of a curve are not unique. In fact, there are infinitely many parametric representations of a given curve. If the curve can be described by a rectangular equation, y is equal to f of x with domain x, then one simple parametric representation is just set x equal to t and y equal to f of t for t and x. So yeah, what they're saying here is if you have something like y is equal to x squared, let's say, okay? So this is going to be our parametric curve, this parabola. Well, one way we could parametrize this curve is just say that x is equal to t and y is equal to t squared. Okay, but however, this is not the only way to parametrize this parabola here, this curve. Okay, we know for a certain parametrization where as t increases, we're moving across the curve. But we could do another parametrization where we move faster across the curve. We progress across this curve as t progresses with different rates or accelerations, etc. There's an infinite number of ways to parametrize the same curve. So in this example, it says, give 2 parametric representations for the equations of this parabola, the equation of this parabola. So the simplest is just to say, here's the curve, and just say x is equal to t and y is equal to, and just replace x with t. That's what they do here. Okay, but another choice is you change from x is equal to t to x is equal to t plus 2, or maybe if you want to progress faster, you could say x is equal to t squared. But how does that affect y if we want to stay on the same curve? Well, you're just replacing x with t plus 2 is what you're doing to get this. So it's like you write the equation of a curve in 2D, 3D, whatever. Then you can pick your x based on how fast, like how you want to progress along the curve. This is just kind of shifted. This doesn't change the standard speed or anything, but you might make x equal to t squared or square root of t or something, and you just input that into the equation to solve for y as a function of t, and you're still on that same curve. Okay, the cycloid. So the cycloid is a really good example of the use of parametric equations. This is going to give us a sense for how powerful parametric equations can be. It really allows us to model a system in a way that it would be very difficult, if not impossible, to do any other way. Okay, so the cycloid is a special case of the trochoid, a curve traced out by a point at a given distance from the center of a circle as the circle rolls along a straight line. So what they're saying is that you have this straight path here, okay, and if this is the start point, okay, well, we pick a point a certain distance away from the circle. It could be on the circumference, and that's what they're saying here. For the case of a cycloid, it says if the point is on the circumference of the circle, then that's the special case of the trochoid called the cycloid. But in general, we can pick any distance we want away from the center of the circle. Let's say here, for example. And so this trochoid curve is just going to be, you think about this line here is kind of fixed to the circle. It's going to roll with the circle. The circle is going to roll along this path. This line is like welded to the circle. And so as the circle rotates, this point here is going to trace out a path as the circle just rolls along. And that path is called a trochoid. If this point is located anywhere on the circumference of the circle, then that's called a cycloid. And we can represent curves like this parametrically, whereas trying to represent them just with like a input-output relationship, input on the x, output on the y relationship would be difficult. Okay, and so parametrically, a cycloid is given by these two parametric equations. It's going to be two parametric equations because we've got, this is two-dimensional. This curve here, this cycloid, it's going to end up being, after a full rotation, it's the circle goes forward and does a full rotation. It's like this goes all the way around, returns back to the ground. That's going to be like the cycloid for one revolution of the circle, and then it'll just restart. But this is each of these points has an x coordinate and a y coordinate, right? It's two-dimensional, but it's just a curve, so it's a single input parameter. And these are the two parametric equations. Okay, other curves related to trochoids are hypertrochoids and epitrochoids, which are traced out by a point that is a given distance from the center of a circle that rolls along a straight line, but on the inside or outside, respectively. So they're saying if we tracked the curve made by this point, that would be a hypotrochoid. If we track the curve made by this point, that would be epitrochoid, and if it's on the circumference, that's a cycloid. Okay, so now they give an example to graph the cycloid, and all you need to do is, it would be difficult to try and get this y as a function of x. You could try and use trig identities, but it would be difficult. But you can still just, okay, plot t is equal to, okay, well, we're restricted to this range of t. A lot of times that's the case with parametric equations. You have a restricted parameter input. Just plot some points and get the curve. There it is. All right. Now, if you feel like you would like to spend more time on parametric equations, we're going to work example problems in the next video, but there's only one section here. This is just kind of like an overview of parametric equations. We go into them a lot more extensively in Calculus 3, multivariable calculus. So in Calculus 3, I really go through it in detail so you can get a lot of practice, work a lot of problems, look at a lot of examples, and really get comfortable with parametric equations. This is more just kind of an overview just to get your feet wet. All right, applications of parametric equations. Parametric equations are used to simulate motion. Yeah, that's by far the most common application of a parametric equation, where t is the parameter is time, and you're mapping a parametric curve, a trajectory in 2D or 3D. If an object is thrown with a velocity of v feet per second at an angle theta with the horizontal, then its flight can be modeled by, so yeah, these two parametric equations. But even not just 2D or 3D, but one-dimensional parametric equations. X of t is equal to t squared minus 1. I mean, you could have something like a conveyor belt, right? A one-dimensional system. You can model the motions parametrically. So one-dimensional as well. Okay, but this is a two-dimensional system. Here are the parametric equations, and let's see. Where t is in seconds and h is the object's initial height and feet above the ground. Yeah, when you get to dynamics, with engineering mechanics, statics, and dynamics, with dynamics, you're going to start off with one-dimensional parametric equations. Motion, the kinematics along a line, that's what you're going to start off with. So like x of t, find the derivative of this, x dot. Map out the motion, find the second derivative, the acceleration. And then you'll progress to two-dimensional kinematics. This would be two-dimensional. So when it comes to equations of motion, Newton's laws, it's parametric. Newton's laws are a function of time because it's mass times acceleration. Acceleration is a function of time. That's all going to be done parametrically with time in the background. So here, x gives the horizontal position information, y gives the vertical position information, right? This is the horizontal information. This is the vertical information as a function of time, where, again, you know it's parametric because we're not graphing t, x, y. At time t is equal to 1, we're here. At time t is equal to 1, x is equal to 3, y is equal to 5. So we're here. No, it's time is we look at it as a parameter in the background. It's secondary to the phenomena we're observing. Okay, but so yeah, here time is in the background, and the x parametric equation is describing this motion here. The y parametric equation is describing motion here. If we just isolated the y equation by itself, we would be watching a one-dimensional point go along this line. Same idea with x. If we just isolated x by itself, we would be watching some point move along this line. But together, using Pythagorean's theorem, you could get the actual r position together at any moment in time. They give you the actual position in the air. Okay. 3 golf balls are hit simultaneously into the air at 132 feet per second at angles of 30 degrees, 50 degrees, and 70 degrees with the horizontal. Assuming the ground is level, determine graphically which ball travels the greatest distance. Okay, so yeah, if we come back here, these equations are general for projectile motion, where you're not considering wind resistance. It's simplified, no wind resistance. The only effect is gravity. So v is the velocity in which the ball is thrown. Theta is the angle in which the ball is thrown. So v is not a function of anything. V is a constant. What you can see is that when it comes to the x position, this factor here is just a constant. V cosine theta. Theta is a constant. It's just the initial angle. V is a constant, the initial velocity. There's nothing affecting the x position because there's no air resistance. But the y position is being affected by gravity. And this accounts for gravity. Now, the initial x position is always at like x is equal to 0, but we can't have an initial height, a starting height. Okay, but don't get bogged down with these formulas, what they mean, how they were derived. That's something we do in dynamics, kinematics. But just try and focus on the application of the parametric equations. So, okay, the golf balls are hit into the air at the initial velocity of 132 feet per second. That's v. And here's 3 different thetas. So we can say theta 1, theta 2, theta 3, the starting angles. Okay. Is there a starting height? Well, no. Yeah, it's on the golf ball's on the ground. So h is equal to 0. Assume the ground is level. So determine which golf ball travels the greatest distance. You just fill out this formula here. And from there, what you're needing to do is set y equal to 0 and solve for t. Now, y is going to be 0 when t is equal to 0, but y is also going to be 0 when t is equal to some other value. That's what you're looking for, because the golf ball is going to do, it's going to start at y is equal to 0, t is going to start increasing, and it's going to come back down. Okay, a golf ball is just this is projectile motion. But we're not accounting for any wind resistance. So when y is equal to 0, what is t equal to? Well, then take that t and plug it back in here to get the distance. Do this with, we have the same v every time, but do this with the 3 separate thetas. So you can like optimize the launch angle to maximize distance, and that's what they do. Okay, now it says, which ball reaches the greatest height? Estimate the height. Well, we could do this analytically using calculus, because the velocity in the y direction is going to be 0 at the maximum height, then it's going to switch to a negative velocity. But we're not getting into any calculus here. They just do a plot and use like a trace feature. You can graph parametric equations with your calculator using MATLAB on like Desmos, whatever. You can just trace and see, okay, which ball has the highest height, which might not correspond to the farthest distance. There's like probably a nice medium between the launch angle, which corresponds to the maximum height, and maximizing the longest horizontal distance. Okay, let's see. Jack launches a small rocket from a table that is 3.36 feet above the ground. Its initial velocity is 64 feet per second, and it is launched at an angle of 30 degrees with respect to the ground. So v is equal to 3.36 feet. Theta is equal to 30 degrees. Find the rectangular equation that models its path. What type of path does the rocket follow? So, yeah, you could just plug these values into the projectile motion parametric equations, and then from there, do the conversion, right? So that's what they do here, and they get these two parametric equations. Well, okay, solve for t, and then plug that t into the other equation. That's what they do here. And they plug t into this and simplify, and there you go. There's the path, the parametric curve, which we know we have a parametric curve anytime we have one input. Okay, analyzing the path of a projectile, determine the total flight time and the horizontal distance traveled by the rocket in the previous example. Okay, so the total flight time is just going to be when y, we start with y equal to 3.36. So when y is equal to negative 3.36 feet, that's when the flight ends because it hits the ground, right? So we can plug this y in here and solve for t. And that's going to be the total flight time. And the horizontal distance, well, we plug that same t into here. So yeah, there you go. That gets your feet wet with parametric equations. In the next video, we'll work some example problems so you can kind of cement everything we just talked about here. But then, again, we go into this a lot more extensively in Calculus 3.